Yes, so the last lecture is on synthetic polymers and synthetic fibers. And so this will be a sort of a part two. The first part was natural fibers, talking about proteins, carbohydrates, and all of the things, biopolymers, DNA. This one's synthetic polymers, so all the different plastic materials that we have for our modern society. What are the forensic details associated with those polymers? So we're going to talk about the monomers, how they're polymerized, and that will lead to forensically important additives, things that we can extract out of polymers to know how they were manufactured and potentially where, what company made this polymer or what process made this polymer. So this is the same, essentially, terminology that we had before, but I put it in this lecture as a review. Also, sometimes these lectures are swapped in order and so on. So we'll skip through the terminology pretty quickly and then get into how we make synthetic polymers. So this is the same outline we've seen before. Last time we did the ones on the left, the biopolymers and semisynthetics, and today we're talking about the synthetic organic polymers. And one way to there's many ways to classify things, as you've noticed. Remember the 5 Ps? Let's review that while we're here. 5 Ps. Paraphernalia. Powders. Pills. Plant-like matter. Precursors. Fantastic. Y'all are good. And I better remember to put that on the final since I quizzed you on it twice. I want to make sure that you, we remember that and you didn't ask. Okay, so, but one way to classify polymers is to classify them with the way they're made. Okay, condensation polymers or free radical polymerization, chain step polymers. And so we had the same slide last time about the different terminology. You have random and block and alternating and graft polymerization. And then the different kinds of linkages. You have linear and branched. You can have dendrimers, which start with like a trivalent or a three, like nitrogen that has tertiary structure and then grow out from that. And if that's branched, then you have dendrites, or these little fingers that come out. And then cross-linking is a super important property of polymers and changing its physical nature. We have the melting point behavior for polymers. And then the difference between natural and semisynthetics are a lot of times based on the physical properties, sometimes the chemical properties, changing their solubility by putting acetates on all the hydroxides and so on. So you can do chemical processing on natural fibers and make a semisynthetic fiber. But today we're going to talk about the synthetic fibers. So the left side of this, so under the synthetic polymers we have different ways of making them. And on the left-hand side we have chain growth polymerization. And on the right we have addition, step growth, and ring opening, which deals mostly with epoxide functional groups. Probably the largest variety of polymers are done with this chain growth polymerization. And the one thing I want to point out is that the chain growth polymerization often require initiators or catalysts. So something that starts the process, and if you'll notice, it's different mechanisms for growing these. Look at these types of chain growth polymerization. You have anionic, cationic, and free radical. Now, most substances, organic substances, don't just spontaneously form anions, okay, or spontaneously form cations. And certainly they don't spontaneously form free radicals, okay? But you can have an initiating event. Think about a free radical event. That easiest one to initiate the free radical is light, UV light or deep blue light. You can initiate that polymerization by shining light on it and creating a free radical pair. Taking that organic compound and putting it up into a triplet state. What is a triplet state? Unpaired electrons. By definition, those unpaired electrons cannot be in the same orbital. Okay, so when you create a triplet state, you have unpaired electrons, and they're probably in different orbitals, which means they might be concentrated on different atoms. And so you have an unpaired electron on this atom and an unpaired electron on this atom, and then one of those can react and start a polymerization process. Okay. Another way to initiate that is with something that creates an anion or a cation, something that attacks a nucleophile and transfers you know, a nucleophile that attacks an atom and transfers that negative charge onto that molecule, then that negative charge can propagate through. Same thing with a cation. It can propagate the cation charge. Now, once you've initiated it, sometimes it's helpful to use a catalyst to keep the polymerization going. And so these catalysts and initiators are forensically important sometimes. So this is an example of a thiophene. So this is actually the monomer here. It's kind of small for you to see, but this is the monomer here. And we have this pre-catalyst. It's nickel. It's surrounded by these diphenylphosphine groups, so bis diphenylphosphine on an ethylene linker. And that nickel is a very active metal. And so it will bring these two monomers together with some bonds and then link them. And so this is the catalyst. And once it goes through this thing, it's regenerated. And so you get a catalytic circle going with that nickel catalyst. It's helping with the polymerization. Now, why is this forensically important? Because when you analyze this, you may still have some of that catalyst left over in the polymer. It might get trapped in the polymer matrix. If you think about making that polymer, you're growing essentially spaghetti, and the catalyst gets surrounded, and if it doesn't get all washed out, then you're going to have nickel in that polymer. So sometimes, even though a polymer is an organic substance, it might be forensically relevant to digest that and look for metals to try to determine what catalyst is there. Some trace catalyst metal that's still in that polymer would tell you what kind of polymerization process was used. And you might find the initiators too as well. So you might find these other compounds in these polymers, even though that might be polystyrene and you know what the backbone looks like and the styrene, that would be easy. You could determine these polymers mostly by infrared. You put a bit of the polymer on the FTIR, the ATR, just press it down, take a scan. The main peaks are going to be the backbone, the polymer backbone. So you can determine what kind of polymer it is instantaneously with a library search on FTIR. So knowing that it's styrene is not an issue. You know it's styrene with one scan of the FTIR. But where did it come from? Who made it? How was it made? Those might be forensically relevant questions. So let's get to know the different monomers associated with the polymerizations and the different polymers that we have in the world around us. So what do you see in all of these monomers? Carbon, okay, so they're organic, typically organic compounds. Double bonds. So those double bonds are the thing that we use to make polymers. Because you got a carbon that bonds to four things, and here we have unsaturated carbons. They're ready to bond with other unsaturated carbons. So you start with an unsaturated system. It could be triple bonds too. And you activate it, and then it starts to go. Some of these go naturally by themselves. Like this one here in the middle. What would you call that molecule? Tetrafluoroethylene. Okay, or tetrafluoroethylene sounds a lot like Teflon, and that's what it is. The trade name is Teflon. But they had this in a tank. The story goes, they had this in a gas cylinder. They were going to do research with it, and they went and turned on the gas cylinder to start the research, and there was no pressure in the tank. And they thought they had lost the material, like it had leaked out, but they didn't think that it had a leaky regulator. And they weighed the cylinder, and it still had as much mass as a full cylinder. And so they knew the material was still in there, but it was no longer in the gas phase. And so then the story goes, they cut open the cylinder, and they found that the Teflon had polymerized to make Teflon in that tank. And so it might have been exothermic, they just didn't notice. The tank may have heated up. In fact, that can be very dangerous. Like I was saying about acetylene, you have to dissolve acetylene in acetone inside the tank so that it doesn't polymerize and make an exothermic bomb. So that's the story about how they discovered Teflon, and they started making it and found it was very chemically inert. And so there's always the question, how do they get something that's inert and doesn't stick to anything to stick to a pan?
Yeah.
And I know the answer to that, and it's with the Hansen solubility parameters. The primer coat after primer coat, and then finally you get something to stick to the Teflon. So we can show, yes.
What about like Teflon tape?
Teflon tape, very not sticky. Yeah, have you ever messed with it?
Yeah.
Yeah. And so it's also used to seal fittings, like in plumbing. So you can buy Teflon tape. It's really cheap. And if you ever need, anyway, there's lots of little things you can find in the hardware store that are handy for chemical research. Just go look through my lab. It looks like somebody took the Ace hardware and kind of sprinkled some of it into my lab. I'm always buying Teflon tape and what we call plumber strap. It's this metal galvanized strap that has holes drilled every inch. And I make all kinds of things out of that because I just get the needle nose pliers and start bending it and making fixtures and everything. But the Teflon tape's a great surface because it's clean and it's inert, and you can actually do like dropwise experiments on the Teflon surface. You can do it on glass, you can do it on Teflon, so Teflon is a fantastic form in that tape. Now you can wrap it around the threads of pipe fittings and screw it in, and it does two things. It seals because it gets gummed up in the threads, and it also lubricates the fitting so you can screw it in farther. So it's this slippery surface and the metal to metal contact, it smooths out that friction. So you can really tighten down those joints with a little bit of Teflon inside. Some of these other polymers we'll see here in a minute where it's listed as to their names, but you've seen a lot of these. Okay, so here's the list. This is kind of like your note card list. So know all these on this page, and they're pretty easy. You look at the monomer, and that gives you the name for the polymer. You just put poly in front of it. So over on the left, up at the top, you have ethylene. Okay, and then so that's polyethylene. And then you have propylene. So then it's polypropylene. Okay. And so here's propylene or propene, so that's polypropylene. We use sort of the older terms, not the IUPAC names. And then here's a chlorine on here, and when you put a chlorine on here, they use the older name, that's vinyl chloride. And so then that's polyvinyl chloride. Notice the double bond is gone. And this is the thing that can be confusing. This is ethylene, and the ENE indicates that there's a double bond, right? But then when you make polyethylene, the ENE is lying to you. It says there's a double bond, but there are no double bonds left. So you're naming it based on the monomer, not on what's in the polymer. So if you think polyethylene is unsaturated, you're wrong. Even though that ENE, you were told inorganic, that means that there's a double bond in there. That's not the case. We've polymerized it, and those double bonds are gone. And here's polystyrene. Now there's lots of double bonds to work with in this molecule, but the most active is the one over here with the methylene groups. And so this is where the polymerization takes place. And so you just have the phenyl group sticking off of that polymer backbone. This makes this polymer have quite a bit of different nature than polyethylene, because polyethylene is fully saturated. Here we have all these benzene groups. And so polystyrene has quite a different nature to it. It's also got quite a bit of different solubility as well. So because of the unsaturated phenyl ring, it'll be compatible with different solvents than polyethylene. One of the most inert polymers is Teflon. That's the brand name, Kevlar, the trademark name here. But that's the chemical name is polytetrafluoroethylene. So this is tetrafluoroethylene, and that's polytetrafluoroethylene. And then here we have acrylic, right? Acrylonitrile. So it's really confusing, these old names. Here's vinyl chloride, and here's acrylonitrile. Okay? And so I don't know really any way to know these old names except to just memorize it. So you just may need to make a note card with these different ones so that you're quick with recognizing what their names are. And so this is the monomer, acrylonitrile, and so this is a polyacrylonitrile. Here's a couple of trade names, Orlon or Acrylan. Then we have methyl methacrylate. Okay, so I guess the methacrylate would be this item here, and then you've got a methyl on there to make the methyl ester. And this is polymethyl methacrylate. This can be extruded or cast into sheets. that are very clear. And so when this polymer is cast into sheets and dried, and the solvent is evaporated, this makes a very clear, hard substance, and that's where we get plexiglass or lucite. Those are the trade names for this. So looking at those substances, you would see in the infrared, you'd see the peaks associated with this ester group. You'd see peaks associated with the methyl groups, etc. Looking at acrylan, also, an inert sheet-like material, you could cast that into sheets and make a hard plastic out of it. You'd see the nitrile groups. Orlon fabric, if it's spun into fibers, you would definitely see that cyano group in the infrared. So remember, the infrared tells you what all the different kinds of bonds you have. And so that, y'all did, we looked at a few different solvents with the infrared, but you're going to just think of your organic chemistry. You had that table that had all the different functional groups and their vibrational frequencies. Now, I'm not going to retest you on those vibrational frequencies, but I definitely want you to know, just intuitively, if you want to tell the difference between any of these polymers, infrared is your best tool. You're going to see the CF stretch, the carbon fluoride stretch, in Teflon. You would not see that in ethylene, right? So you can easily tell the difference between Teflon and some kind of white, like milk jug material. So they're both white. Which one is which? You could just put that on the IR and you'd see a CF stretch for Teflon. You would know that that's not high-density polyethylene or high-density polypropylene. High-density polypropylene and polyethylene have super simple spectra because there are no oxygens, no fluorines, no chlorines. All you have is CHs. So you have a lot of CH2 stretches, and that's about it. A couple of carbon-carbon stretches, and that's what you have. And then down here, polyvinyl acetate. You have, again, the vinyl group, and then it's put this acetyl group on there. So polyvinyl acetate. Here are some more. Polyisobutylene, which is butyl rubber. So the isobutylene, here's an isobutane group, but it's butylene, so it has an unsaturated bond here. And so you've got a lot of methyl groups and some CH2 linkers. And then this isoprene, that was in the latex from tree sap. And so you can pull that tree sap out, start to dry it, and even upon drying, you'll start to initiate some polymerization. So that tree sap will start to become polymerized and make natural rubber. And then polybutadiene, so here's butadiene. So polybutadiene, it still has some double bonds, and so does natural rubber. This unsaturated nature of polybutadiene and natural rubber really make them, when they make gloves out of them, this is what makes these gloves dangerous, in my opinion, okay? Because organic solvents are attracted to those double bonds. There's a large electron cloud, it's polarizable, like seeks like. And so this gives that natural rubber a way to just absorb organic solvents. And so if you're working with organic solvents, never use latex gloves because they're not protecting you at all. Okay. Always use the nitrile gloves. Those nitrile gloves, the nitrile groups are more chemically inert and more different than normal organic solvents, and so they're more impervious or resistant to organic solvents. So the nitrile gloves will not absorb organic solvents as much as natural rubber. All rubber material or all of these polymeric materials have a breakthrough time, and it's based upon the thickness of the glove and the material of the glove. So if you're going to have more of an immersion experience with your gloves, like you're having to reach down in the solvent, you need a much thicker glove. Okay. And so they're in thousandths of an inch. They call that a mil. And so you can get 7 and 10 mil gloves that are pretty thick. The ones we have in the lab, we buy the cheapest gloves we can because it's mostly just for splash protection. You don't want, you're pouring something and it drips down the side and it just barely touches the finger. It's not immersion. But I had a student who was working on cleaning these beakers with toluene, and I thought that they would just naturally scrub. No, this student had like a Brillo pad thing and was reaching in the beaker with toluene and was scrubbing with toluene and not thinking about the breakthrough time on the gloves. And so I was watching and I said, whoa, wait, are you immersing? And she goes, yeah, these gloves aren't very good. She picked it up and the finger fell off. Like it had totally unraveled the polymer and the polymer just failed. And I said, we've got to get you some different gloves. And you can stop digging your hand in the beaker of toluene. So, use a brush. Use something, that extends beyond your hand so that you're not immersing your hand in solvent. Okay. It would have been 10 times worse with rubber. You could probably squirt toluene on a latex glove and it just fall apart in front of you. It'd be fun to try. Yeah. And so, one of the ways to make natural rubber a little bit more chemically resistant is to chlorinate it first. And so this would be, again, a semisynthetic, really. You can pull that isoprene out of tree sap, process it with chlorine, and then make polychloroprene, neoprene rubber. A lot more water resistant. And then one of the best, the machinable plastics is Delrin. That's the trade name. And so here's Delrin. It's polyformaldehyde. So you just take formaldehyde, there's a double bond, and then you're basically making a polyether. Okay. So polyoxymethylene or polyformaldehyde would be a couple of different names for that. Any questions on any of these? Anything you'd want clarified or applications? Okay, let's move on. Here's a nice little graphic I just put in the notes for your benefit. This is the chemistry of superglue. I love some of these things. I see them on Instagram or whatever, and I'll pull them down. So they're fantastic. So here's the methyl cyanoacrylate. So here's this group. We've got this ester group and also this cyano group on here. And then it's polymerized. A lot of these really fast-acting molecules have a propensity to react with water. And so this is interesting. We had very low humidity environment at Pentex, and some of these glues that required a lot of moisture to activate were less than ideal in a low humid environment. So we had to have it below 15% humidity. So it was extremely dry. And that's uncommon. I mean, even in the north where it's cold, it's still uncommon to be that dry. And so, the formulation of these glues is based upon normal conditions. And so you use superglue in your house is of a moderate humidity, and actually superglue is using the humidity in your room to get started. And so if you're in an extremely low humid environment, it doesn't have the moisture to activate. But this one activates, and this kicks off the reaction, and then this is incredibly active. This is a great nucleophile, and it will attack the other methyl methacrylate molecules, but this nucleophile will also attack protein. And where do you have protein? Yeah, your fingertips. And I mean, it is incredibly fast. Have you ever used superglue and gotten your fingers stuck together? Who hasn't? I mean, if you've used it, you've touched something and you're like, oh great, now the cap is stuck to my finger. And you got to get it off there quickly because those reactions, those bonds are forming, very fast. And I have had some painful situations where I didn't get it off quick enough, and now the cap is stuck to my finger. I'm trying to pull it off, taking the hide with it. Because it's chemically, covalently bonded to that dead skin layer. And so when you pull it off, you're not breaking the polymer. You can have adhesive failure, and you can have substrate failure. So how you break apart glued objects is it's a battle between the strength of the glue and the strength of the substrate. And so in the case where I've got my finger glued to a plastic cap, the weakest link in that 3-component piece, you've got the cap, you've got the glue, you've got my finger. The weakest link is that dead skin layer on my finger. That's going to break first. And so you pull and pull and you just rip the skin off. And hopefully it's just the outer layer and that you have some calluses. I don't really have many calluses, so it hurts. Yes?
Usually when I do it, I use acetone to get it off.
That's pretty good. Yeah.
Yeah, but I always get concerned, like, since I'm kind of like taking some of my skin off, it's acetone gonna seep in.
Yeah, and so that's the thing. Whenever your skin comes in contact with organic solvents, most of the time that dead skin layer protects you, because those solvents aren't necessarily compatible with layers and layers of protein. But some solvents go right through the skin. They like the protein, they'll go right in to the dead skin layer and then end up in your bloodstream. And there are actually some transdermal, the patches and things that are based upon that science. They'll tailor the adhesive where the medicine is in that patch with the skin layer and work on that transdermal transfer of the active ingredient. But yeah, acetone or gasoline or any of those things will go through the skin to some degree. In fact, you could get a lethal dose by being immersed in gasoline. I mean, if you were like in an accident where your body was soaked with gasoline, you really have to get that off. You have to strip down and get that clothing off and hopefully get it to evaporate out of your skin layer before it goes into your body. Okay, so it's not guaranteed to be a lethal dose, but it could make you very, very sick because it goes through the skin. I'm more worried about the impurities, though. I mean, acetone is probably going to be metabolized to some extent in the body, but what else did it pull in with it? So let's look at these chain polymerizations. This is a lot of different mechanisms. I mainly just want you to think about how we would classify these and what kind of impurities we might have. And so here again we use nucleophilic attack. This is that acrylonitrile reaction, and it's going to attack cellulose as well and skin, but it's not going to work very well on some substances. So trying to use superglue on a milk jug or on a polyethylene bottle, so you want to glue something to one of those items, it doesn't stick very well to the fully saturated polymers. Okay. So there's just not enough of that nucleus exposed when it's surrounded by all those hydrogens, or with the Teflon, it's not going to stick to Teflon. So superglue does not stick to everything. It says it sticks to plastic on the bottle, but that's what is plastic, right? How many varieties? That's what we're talking about. How many varieties of plastic are there? It's not going to stick to every plastic. We tried on this one experiment, we tried to put a rubber septum on so we could take a gas sample through this carboy and then have it seal back up. So we had a polydimethyl siloxane septum, and we were going to glue it to polypropylene carboy. And we used super glue and stuck it on there, let it dry, and we came in and it just popped right off. So we had a failure to adhere, so that super glue did not stick to the polyethylene. And because you can make covalent bonds and you can also entangle polymers. So the secret to cohesion is entanglement. And so you want those polymers to entangle with each other. So you need a solvent that activates both surfaces. So you could probably get it to adhere, but you would need to have some sort of solvent process for gluing it on. The chemical process did not work. And so when you link these together, you see all of these cyano groups, which are very chemically inert. And then you have all of these methacrylates, okay, which are not as chemically inert. But the protein in your sweat glands gets deposited whenever you leave a fingerprint. And so whenever you use this superglue vapor, you have active acrylonitrile that lands on that fingerprint and reacts with the protein in that fingerprint. And so you will build up layers of this superglue molecule on the fingerprint. And once you have this pattern of reaction and reactivity, then you can more easily dust that, and the dust will stick to where the superglue is, and you can get contrast. And so that's what's going on with the detection of very small amounts of fingerprint grease and protein using the superglue activation. So let's look at cation growth. Here we have boron as an initiator. So again, that may be forensically relevant. So BF3, that may be an impurity in this polymer. It would tell you, okay, this was polymerized using cation chain growth. So you have a boron that's electron deficient, and it sees that double bond, and the double bond says, hey, a nucleus that's not, it's open for business. We'll attach to that nucleus, and the BF3 is an anion, and now there's a cation over on this tertiary bonded carbon. Very, very stable cation. But then another set of electrons sees that cation and makes a bond. And so then we've grown that polymer. Now we have two monomers and a cation. And so this can grow, grow, grow. And so that would be then chain propagation. You just keep adding double bonded monomers to that cation, and the cation keeps hopping down the chain. So that's cation chain growth polymerization.
What is the initiator go?
Yes, so that's a great question. It's going to react with other impurities in the process. It might sometimes they get attacked. You know, what we're looking at is the relative rates of reaction with this double bond and this B minus, right? So you could have a chain terminating step if one of these B minuses reacts with the cation, okay? And so you might have, let's say, an odd reaction where a fluorine is transferred over. Okay, so this would be the main reaction that happens, but these side reactions that wreck the process eventually terminate the chain propagation. Okay. So you'll have, very small amounts of fluorine, carbon-fluorine bonds, or you might have a small amount of boron. Let's see, oxygen maybe get it in there and makes borax, so boron oxides. And so it can be poisoned, I guess is the point. But at the beginning, you have so much monomer that this is the dominant step. But then as the monomer concentration starts to drop, then those side reactions become more probable. And so then eventually it just gets poisoned by oxygen or by chain terminating reactions. But initially, you have so much monomer that you're just flooding the system with chain propagation. But that's a great question. I'm going to give you a sticker for that because that was thought out. This is my favorite. I don't know why, but I just love free radicals. I mean, I don't know. I'm not a radical, but it's just really cool to me. Your peroxides are the easiest things to split apart to make two free radicals. So that's one of the ways that peroxides are super reactive, and especially in the atmosphere. They make photochemical smog because light can hit them and make two free radicals, and then they start interacting with organic substances. And so any double bond can be attacked by one of these radicals. But you'll have this radical initiator. And so that may be a substance that's very different than the polymer. So again, here's your forensically relevant material. Whatever this R group is may be so different than your polymer that it's detectable. Okay? And so here now we have, remember from Dr. Arnie or whoever you had for organic mechanisms, the single-headed arrow? So one electron from the double bond reacts with this free electron from the free radical, and then this other electron goes onto that carbon. So those are single-headed arrows or half arrows. What did he call them? Or the organic prof? You don't remember? Yeah.
Oh, he didn't call him.
Double-headed arrows, so like the double-headed arrow. So I don't remember what they call it, just a half arrow. But it's a single electron. I remember that. I took organic chemistry in 1989. But I do remember that. And so then you end up with this now the radical is propagated onto the next carbon, and it's ready to do the same thing to another monomer. And again, it's a balancing of reaction rates. So since there's so much monomer in the pot, then this is the dominating reaction. And so we've added another monomer to the link, and the chain has grown by 1 unit. And do it again and again and again. Now this one is the easiest to understand in terms of chain terminating steps, what stops the process. Because this piece right here can link up to another free radical and end the process. So the free radicals can meet, and now you're done. So you have this competing rate of chain propagation and chain joining or chain termination. And so at the beginning, you have an enormous amount of monomer and very little free radical in the pot. You just put a little initiator, some peroxide in, it initiates the process, you start polymerization, a lot of monomer, but then the monomer concentration starts to drop, and the number of free radicals in the pot starts to grow, and then you start getting a faster or higher number of chain terminations. And then the process shuts itself down. And so ways to deal with that is how you fine-tune the length of those chains. Okay, so if you put in a lot of initiator, then you start out with a lot of free radicals really early on, and the monomer concentration drops quickly, and you get a lot of chain terminations. If you want to grow a long radical, you use just a little bit of initiator, so that chain can grow a long time before it ever finds another free radical. So just tuning the amount of initiator that you put in and making sure oxygen is out of there and that it's a dry situation, then you can grow longer and longer polymers. Polyethylene, again, you can make this with the free radical polymerization. Now, one of the things that free radical can do is it can abstract a hydrogen. And so it's showing double-sided arrows, and that's not cool. Okay, so this is just a single electron hitting that hydrogen, and the hydrogen bond is getting split, and that is putting a free radical down into the middle of this chain. And so this is branching. And so you can fine-tune the amount of branching that you propagate by putting in more free radicals or less. And then you can put in extra monomers like ethylene, and you can start putting branches onto the backbone. And that changes how tightly you can press this polymer into a shape. So if you've got really long chains, they naturally lay down, and you can press that into a tight space. And so high density polyethylene is what we have for our milk jug. That's one of the most common ones, high density polyethylene or high density polypropylene. So it's not been branched a lot. And those long chains can rest next to each other and be pressed into a thin layer that's really strong and chemically inert, because you don't want your milk reacting with the jug. Okay. But then if you do a lot of branching, so you put in a lot of free radicals and maybe even some extra peroxide, it starts abstracting hydrogens and making these branch points, and then you put in a lot of extra material to join with those branch points. Then you end up with a lot of short chains and short branches, and that's low density polyethylene, and that would be a soft polyethylene. And that's what you would want for filler material. You know, again, it's not going to pack tightly, but it's also going to be soft. And so if you could make a polyethylene product that was soft to the touch, maybe you'd want that for carpet or for microfiber cloths in some manner. So lots of branching. Again, it makes it non-dense, and it's a decent insulator. So, chemically inert insulation. It's not going to absorb a lot of water. So that's fantastic. And then finally we get to ring opening polymerization. This uses the epoxide functional group, and that's the origin of that term epoxy. So if you ever wondered what epoxy was, you have this epoxide group. So you've taken a propylene molecule that had a double bond in it and reacted it with oxygen. So oxygen comes down on top of that double bond, and the double bond opens up and grabs hold of the oxygen. And so you have a three-membered ring with oxygen in it. And so that's the three-membered ring. And you can put that on, like I said, we put it on a propylene in this case, but you can put it on any kind of double bond and make an epoxide. You can do this in two ways. You can react it with a Lewis base or a Lewis acid. Okay, so Lewis base has lots of lone pairs, and it can attack, and then that ring opens up, and you end up with the negative oxygen on the end, which is a Lewis base, and then it comes up and attacks the next monomer, and the next monomer, and the next monomer. So it's using kind of an anionic propagation by coming in with an anion and starting that process off. Or you can have something with the Lewis acid. One of those examples was the BF3 of making cation propagation. And so this is going to essentially connect to that oxygen, creating a cation because it's bonded to three things. And then that's going to come in and attack underneath, and you're going to propagate through that epoxide. So using that cation on the oxygen is how you're going to propagate this. The next one's going to attack this carbon down here. Most of these are two-part molecules, so you'll have the what they call the what is it? The resin and the initiator. So you'll have the two-part epoxies, which have, again, this is a very reactive functional group, and so you want to isolate it so that it doesn't start to polymerize. And so you can have this active epoxy in one group, and then a different part that's going to react with it in another. So you mix this together and start stirring. And you stir it to mix it, but it's starting to react right away. So it's polymerizing while you're stirring. But you're trying to mix it effectively so that it can react through the whole material and then stop and make a hard plastic. It's amazing how well they time these things. They put the right amounts of each of the parts in there, and they can tell you that you can stir it for like 2 minutes, and that's a slow setting epoxy, somewhere like 30 seconds. You mix it for 30 seconds and it starts to get hard. If you've ever used Bondo to repair any gaps or holes in your car, we had a blowout on our trailer tire, and the rubber from the tire actually rubbed a hole in the plastic fender, like tore right through it. And so I had a hole in my fender. Now my trailer is connected to the outside world, and mice and everything else can crawl through that hole. And so I had to seal this up quickly. So I told Thomas, let's go to the store. So we went to the AutoZone and got a little thing of Bondo. And I'm reading the instructions, and it said, like, stir for 30 seconds and start to smear. It has a little screen. You put this screen on there, and you smear this plastic on there, and it hardens, and now you've got a plastic shell. Okay. And I think it may have been 1 minute. It said, can work up to 1 minute. So I was going to stir for just under 1 minute. Well, I got the time wrong and stirred for a minute. And my stir stick's going, and we're talking, 45, 46, 47. I get up to what I thought was 50, and I was going to start to spread it out. I must have been 10 seconds slow, because I was like 49, 50, and my little stick stopped. And I pulled out this little popsicle of Bondo. It was hard. It wasn't hard as a rock, but there was no spreading it. It was done. So great. I'm glad I didn't use the whole can, because I used half the can, and my son was laughing. So then I only stirred quickly for 30 seconds, and then had 20 seconds to smear it onto the mesh, and it all worked just fine. It was a little ugly because you have to go fast, but that's the thing with Bondo. You make an ugly surface, and then you sand it off, and then you paint it. Okay, this is down in the wheel well inside the cabinet. We didn't bother painting it. But it's amazing how well they have this process down. Now, there was no time for the initiator or any of the catalysts or anything that they added to that to come out of that plastic. I stirred for 50 seconds, and it hardened. And so I guarantee if we were to scrape some of that out and do an ether extraction, we might be able to extract some of those minor components. So that's a wonderful tool to use as ether extraction to get those trace components. because you think of how well a rotovap works. Okay? I mean, you could grind up a chunk of plastic, stick it into an Erlenmeyer and shake that with ether and extract all of these minor organic compounds, put them in a rotovap, evaporate that down, and then reconstitute it with a little acetonitrile or whatever you want to use for your chromatography experiment, and then you could do chromatography on that and see what those components were. So that would be a way to get those minor components. Would be an ether extraction, evaporate off the ether, reconstitute in your analysis solvent, a small volume, and you would swirl that around in the collection, in that rotovap flask, and then pull that out and inject that into a chromatographic experiment. Now, step growth polymerization does not always use an initiator because these reactions just occur in nature. So you've got a OH group and an amine group, and you can lose water. So one of those hydrogens goes with this OH. And so we'll just take this away and one of those hydrogens away, and that makes water. And now the nitrogen carbon bond is what's left. Now the one thing that bothers me about this is the way they've done this on the cation. And so this right here just scratched through one of those. Okay. And so I'm just going to draw an amine here. And so you end up with this amide linkage. This C double bond to O, single bond to N, single bond to H. So you've lost that cation. Let's just get rid of that cation. So ammonium, is a primary amine reacting with any kind of OH, but especially a carboxylic acid will give this amide group. So an amine and an alcohol, or amine and an acid group. You could also do this with chloride, where you have a chloride on an organic molecule reacting with an acid, and it can take away water, or HCl. An acid reacting with an alcohol, making an ester, and an aldehyde reacting with an alcohol. So these are all different condensation reactions where they leave behind water. And the nylon is one of these. We have the NH and the carboxylic acid condensing to form water, so the amine and the acid reacting. And we talked about this reaction before. Now this one is nylon 6. It's an amine on one end and an acid on the other. And so it just reacts head to tail. And so that's nylon 6 because it's just one 6 carbon molecule. But you could also react it with the adipic acid, which is a diacid, the 6 carbon acid, and then the hexene diamine, which is the diamine on each end of hexane. Again, condensation, here's the amide linkage right here. And here's the other one kind of in reverse. And so that's nylon 6,6 because it's a hexane, diamine, and the adipic acid. So that's what the 2 6s are. And then Kevlar. You've heard of Kevlar. It's a fantastic polymer, a very, very rigid and hard polymer. They can spin this into fibers. And the thing that makes Kevlar unique is this amide linkage that gives you this property of the hydrogen bonding and then the crystallization of the structure. And so the nice thing about this is it has both pi to pi stacking. So this would be pi stacking. And H bonding. Both of these are intermolecular attractions between the chains. So they give this polymer strength, but when it gets hit or insulted, those associations can break and absorb energy. Right? So you've got this fiber and it gets pulled really hard, like in a parachute situation, and that those chains can readjust and absorb some of that energy without breaking. Or they get hit like a bullet hits it. And what is a bullet doing? Well, right where it hits, of course, it's giving an impact, but it's also stretching all of those fibers. And again, they can absorb that energy by breaking the pi-pi interactions and by breaking the hydrogen bonds. So that is key to protecting the backbone of the polymer. Think about what has to happen if you have a bullet hitting a fiber. You've got to absorb that energy somehow. And you can absorb it by breaking bonds, covalent bonds, or you can absorb it by breaking hydrogen bonds and pi-pi interactions. And so that's what makes this polymer so fantastic, is because you can break those pi-to-pi interactions, and every one of those breaks takes energy. And the hydrogen bonds also. Whenever you break those hydrogen bonds, you lose energy. So the kinetic energy of the bullet is being turned into the breaking of these hydrogen bonds and pi-pi interactions. And it stretches the fiber, but we're burning up all those energy units by breaking those non-covalent associations and protecting the covalent associations. Now, some of those covalent bonds do break, but fewer break in Kevlar than would break in, say, polyethylene. So that's one of the wonderful things about this particular polymer, and that's why it's such a strong makes such strong fibers. Now here's some of the additives that we have that would be forensically relevant. So this one in particular, bisphenol A. Okay, how many have heard of that? You heard of BPA? BPA, bisphenol A, that's what BPA is. Okay. What have you heard about it? Toxic, okay. What else have you heard?
Don't buy water bottles.
Yeah.
Water bottles, okay.
Don't microwave it.
Don't microwave it, very good, yeah. And so if your plastic Tupperware has BPA in it, you know, what does BPA do? Well, it's a monomer, okay. It's for these, what do I want to say, these AB type polymers, you know, where you have molecule A, like phosgene and bisphenol A reacting. Here is a great example of a step growth polymer where this chloride and this hydrogen leave and make HCl. Here's the HCl is lost. And so then you have this is the bond that's formed. And that's lexan, a polycarbonate. Okay, but that's not necessarily you know, something in our dishes or whatever. But you can have this same kind of thing happen with ethylene glycol. So you could react this with ethylene glycol, with bisphenol A, and make with this ethylene glycol a polyethylene polycarbonate. And so you can have this reaction with polyethylene and bisphenol A and make a polycarbonate substance. And again, that's a very processable plastic, and you might have a little bit of that reactant left in it. So BPA would be the reactant that's left over. And so you certainly can make BPA-free plastics by using some of these other tools, like toluene diisocyanate, melamine, dimethyl terephthalate. And so this one, polyethylene terephthalate. So here's a terephthalate molecule. Okay, polyethylene. And so this right here is PET, polyethylene terephthalate. And that's probably the number one plastic used in water bottles and Tupperware, clear Tupperware containers. It's also a component of Dacron. So notice that the functional group here is an ester. And so another name for that is polyester. Okay, and so that's sort of a generic term. There's lots of different kinds of esters that you could have. And so they're all sort of in the category of polyester. but this would be particular one, polyethylene terephthalate, PET. Now, Dacron, that's spun into fibers, like for clothing, right? So water bottles and clothing are essentially the same polymer. And so my mom went to something in Fort Worth. They had a big deal at the museum. Took my kids there, and it was a big display by Coca-Cola. And it had a T-shirt, or Coca-Cola had branded it, and it said, "I recycle my water bottles," and all I got was this T-shirt. Okay. And sure enough, when you recycle a lot of these plastic water bottles, they take that polymer, and there's a big push not to reuse it for drinking water, right? They don't want to reuse containers for the same purpose, especially containers that hold liquid, because you never know what kook put whatever in that bottle. So they don't want to try to take a chance on someone putting arsenic or something in one of those water bottles for whatever reason, and then it going into the system and just getting steam cleaned and drinking water put back in it, and you've still got trace junk in there from some yahoo that put something in there that was nasty. Okay? So they don't like to reuse drinking containers for drinking containers. So what are you going to use all that polymer for? Well, think about all the T-shirts that we wear. You know, it's a huge business. And they like the polyester fabric. It's wrinkle-free. So they take water bottles, reconstitute that polymer into a thread, and then blend that in with natural cotton and make polyester blended fabrics. And then those go into T-shirts and all kinds of things. So you're probably wearing a lot of water bottles. Okay? It just looks different, you know, to our eye. A Melmac, this is interesting. This is a melamine and formaldehyde. And look at this molecule. It's got lots of functional groups that it can react with. And you can react that with a small molecule like formaldehyde, and you can make these sheet-like polymers. So this can make fantastic coatings. And Melmac is a great automotive coating. It's very chemically inert, and it's very hard, okay, because of the nature of this sort of planar molecule as it grows. And so you have these sheets in this top coat, very long-lasting top coats. Now this melamine, as you might imagine, there's a lot of automobiles in the country. And so there's a lot of melamine being used. Look at all the nitrogen in melamine. This was in the news about 10 years ago. May not have been that long, but I always underestimate how long ago it was, so I'll say 10 years. There was a big thing with pet food. Iams and other companies. It wasn't any one company that was in trouble, but I remember Iams was one of the biggest ones, that pets were having kidney failure. They're eating this pet food, and it was making oxalic acid and some other compounds that were wrecking the kidneys, and they were dying from it. So you had people's pets, dogs and cats, dying from kidney failure, and they traced it to the pet food. And it wasn't any one particular brand, so they had to go up the tree a little bit higher to the supplier of the grains that were used in that pet food. And they traced it to China, to a particular company in China that was selling to all these different pet foods. Now, how's that related to melamine? Well, these pet food companies are real particular. We want a certain amount of protein in our pet food so that we can advertise it contains high protein pet food. And so there's a test. We're going to test that for protein. And the test for protein was fooled by melamine. So this company was just dumping melamine into their feedstock and sending it on to the pet food companies. And they were running the protein test, and melamine was a lot cheaper than protein. And so they were getting high numbers on their protein test. So they were faking the test by adding in melamine. But then downstream, when the pets were eating that food, the melamine was reacting in the body and causing compounds that caused their kidneys to fail, and the pets were dying. And so this was huge, and the Chinese company, the president of the company who knew about it, was in big trouble. So I think he actually got executed for it, but it was problematic. Yeah, so not quite what we do in this country. Yeah, so this is BPA. Now, we said that it was toxic, okay? And I was thinking about this. I was like, there can't be that much BPA in these substances. and the toxin is the dose, right? So how could it possibly be having a physiological effect if it's at such low concentrations? Now, yes, you might have chronic effects, right? A small amount each day, every day of your life could lead to some chronic problem, but it wasn't enough to make somebody sick. I mean, we're putting this in to keep rubber soft. We're putting some of these plasticizers and some of these compounds even in like baby bottle nipples, because it's nice soft rubber. And so definitely babies are ingesting this and they're not getting sick. What we're seeing with BPA is this. It's not an acute toxin, but it's an estrogen mimic. And so it binds in the same spots that estrogen binds. And so when you're dealing with a hormone, the toxin isn't the dose, because the hormone is like a light switch. I don't have to do much with the electricity in this room. All I've got to do is come over here, stick one molecule here, one there, one there. And I've had an effect on the whole system. So hormones in the body are unique types of molecules. They act like switches for whole systems of behaviors. I mean, that's what happens in puberty. Child before puberty looks one way. After puberty, a different way. And we're talking picograms of hormone. Think of the physiological changes. So a hormone mimic is a whole different ballgame. And so when they discovered that this was a hormone mimic, then they said, whoa, we've got to really change how we deal with this, because it's not just an acute toxin where you ingest it up to an LD50 and you die, or whatever. There's this range, normal toxicological interaction. That toxicological curve now is moved down to much, much lower doses, because it's messing with the endocrine system. Let's talk now one more thing about the properties, the physical properties of polymers. If it's a curly, just think of hair. If you've got curly, coily hair, you can't push it down, right? But if it's straight hair, all that same amount of hair fits in a small space. And that's what's going on with polymers. Exactly the same thing. Now, over time, polymers can line up and crystallize. So this is an example of a random polymer, but all of a sudden forming crystalline domains. And so this crystalline domain is going to be hard, and the rest of this is going to be soft. Now, if this is a polymer that should be flexible, and expand when it gets hot and cool when it gets cold and not crack, then you want it to be soft and pliable. If it starts to crystallize, then when it expands and contracts, you may break some of these soft regions and you might form cracks. And so this thing could crack from one hard region to another by just breaking a few of those chains. And so we really want to hold this crystallization back for flexible or soft polymers. And this is the number one reason why we use plasticizers. So the term plasticizer is to keep it plastic, not crystalline. And this is one of the most common plasticizers, dibutyl phthalate. So this is the phthalic acid is this benzene ring with a diacid on it, and then the butyl part is this chain on the end. So the dibutyl part is here, and the phthalate is there. And that is put into the plastics when they're formed into shape, and that keeps them flexible and pliable. Guess what we put in Armor All? More plasticizer. So you spray that on your dash and on your tires and so on, and you're putting that plasticizer back in because over time it evaporates and comes out. In fact, why do you think a new car smells different than an old car? It's the plasticizers. So you love that new car smell. It may not be the greatest for you. I don't know. They haven't said anything, but it would be a big deal if this dibutyl phthalate ended up being an estrogen mimic or something like that. Then we'd have a big problem with new cars, But I'm not trying to scare anybody. I'm not saying that is. But the point is they have this plasticizer in there because that plasticizer gets in and it'll keep this crystallization from happening. if those plasticizer molecules are lubricating those long chains and not letting them get so close together that they snap in to a crystalline formation. I mean, you think about polyethylene. How could you crystallize polyethylene? Right? It's just CH2s, up and down, up and down, up and down. But if you get them close enough together, you could have CH2s come together where they just line up. Now you say, well, that's not really a hydrogen bond or anything. It's CH2s in between CH2s, and there's really no chemical bond there. But you don't have to have a chemical bond for something to really hold together tightly. In fact, think of zippers. Zippers don't have a chemical bond, but they're put into each other to where they link together, and now it's all of those little weak friction connections that hold together that zipper. And so ethylene molecules can zip together. But what if you were to put a dibutyl phthalate in there? It would wreck the zipper, wouldn't it? And so adding plasticizer in there keeps those molecules from crystallizing and zipping together. And then we take that polymer, we process it. This is sort of the industrial process for making fibers. We make pellets, we pour them into these extruders, and then we can make films. We can put the solution in there and actually have it start polymerizing or drying in these things, and then push it through a spinneret. And these spinnerets can have these different kinds of shapes, and we can spin these into fibers, and these are the different kinds of fibers that we can make. So this is from a company that makes different fibers, and you can see the different cross-sections that are available just from this company. You can make really boring, solid, round fibers, or something really cute like bow tie cross-section, or this one, crazy spinneret. I mean, it just looks like an amoeba, right? And that one is fantastic because it has deep grooves. It makes a good filtration, insulation. Material can get caught in those grooves, and so it's a good wipe, it's a good filter. So companies custom make these different cross sections of their fibers. And again, if this was in forensics, that would easily be discernible as different than this, or a round fiber. So looking at those cross sections might be important. So microscopy is still a huge tool in forensic science. Get down and look at it. Chemically, if you put that on an FTIR and squeeze it, polyethylene, say, you put that on an FTIR, polyethylene, you're a chemist, and you say they're the same fiber, but you never used a microscope. So you're totally screwed up. All you had to do was look at the cross-section and say, these are not the same. They're made out of the same polymer, but there's more to it than just the chemical properties. There's the physical properties that you need to look at. And so, saying this is chemically the same as that is one thing. That might tell you it's the same company, but those shapes under a microscope would look completely different. And then even inside the fiber, you could see sometimes they have spinnerets inside of spinnerets, and you could get this trilobe shape inside a round fiber, or even the company logo or name. Why would you want these kinds of fibers, these multi-component fibers? Maybe just whatever properties that they have. Maybe one's colored and the other's not. You have one for strength and one for what other properties that you want. So you can combine fibers. It's just an incredible amount of science going into fibers. And all of it might be forensically relevant. So fiber evidence is really a fantastic tool. If you find, carpet fibers at the scene, and you find those same carpet fibers all over the shoes of a suspect, you can say it's consistent with that person being in the room. Then you would want to do research on that carpet to see, was this carpet sold to 1 million different places on Earth or just 3? Was this a special kind of carpet? So you're just narrowing things down and drawing smaller and smaller circles to try to isolate this suspect or exonerate that suspect. So as a scientist, you don't care whether it's guilty or innocent. You're just trying to isolate the data to say it is, consistent with this person being there or inconsistent with that person being there. So we are done. Yes. So I've really enjoyed this semester. It's been great. Really, this whole year we've been together since September and longer. So